Hello everyone and welcome back to Math 127 Pre-Calculus 2. So in the previous chapter, we have studied polar coordinates and vectors. So today, we will begin with chapter 9. So where we will explore the family of curves known as the conic section. And we will start with one of the most common conic section, which is the ellipse. So you may already be familiar with the shape of an ellipse. It's similar to an oval, but in mathematics, an ellipse that has a precise geometric definition and several important properties um, that allow us to graph it and write its equation. So by the end of the lesson, okay, all right, so by the end of the lesson, you'll be able to graph ellipses centered at the origin and away from the origin. And then also we will write the equation in standard form, identify important features such as the center, vertices, foci, and axis, and solve real-world applications involving ellipses. Okay, so now let's go ahead and start it. By the way, I usually say foci. Okay, if you're saying it as foci, that's fine. Both of them are correct anyway. Okay, so let's begin with the definition. Okay, so as you can see, an ellipse is the set of all points in a plane where sum of the distances from two fixed points is constant. Okay, so those two fixed points are what we call the foci. Okay, and the a plural form for that would be again the plural form of focus. Okay, which is the foci. So the midpoint between the two foci is what we call the center. So we do have here the midpoint. Okay, and that would be the center along with, in this case, a horizontal line. Okay, so and then as we examine the diagram, notice several important parts of every ellipse, especially with those terminologies. Okay, all right, so we do have the center. Okay, let me see. Yeah, okay, there you go. We do have the center. Okay, we do have the vertices, and we have the major axis. That would be again wherein the major axis, its endpoints are the vertices. Okay, and then we have there the minor axis, which is perpendicular, of course, with the major axis. And then the foci, and we have okay, the foci over here. Okay, all right, then similar with this another illustration here. So one important observation is that again the major axis, like I've mentioned, always passes through the foci, and then the endpoint are of course the two vertices. So understanding these parts first will make graphing much easier, okay, later in this lesson. All right, okay, so now let's go ahead and recognize. Okay, let's go ahead and recognize the equation of an ellipse. So there are two standard forms depending on the directions, depending on the direction of the major axis. All right, let me just go. Okay, there you go. All right, if you have a major axis that is a horizontal, okay, major axis that is a horizontal, so the equation is x squared over a squared plus y squared over b squared is equal to 1. Okay, again, where a and b are always a positive in value, and then we say that the square of the square of a is always greater than the square of b. Okay, and then once again, this would be our standard equation of the ellipse if again the major axis is a horizontal axis. Okay, now for the vertical major axis, the equation would be x squared over b squared plus the y squared over a squared is equal to 1. Okay, so by going over with value of a squared and then the b squared there. Notice something very important, okay? So the larger, the denominator always belongs to the major axis. So as I have mentioned that a squared is larger than the b squared. So as you can see here, it's the denominator of x, which is again, x is related with a horizontal axis. And so that major axis is a horizontal line. And then as you can see here, the a squared is below or is a denominator of y squared. And so we do have here a major axis that is related with the y-axis, which is again a vertical axis. Okay, so this is one of the easiest way to determine whether the ellipse is horizontal or vertical. Okay, so another relationship that you will use throughout this section is the c squared is equal to a squared minus b squared. So this formula helps us locate the foci once we know the lengths of the major and minor axis. Okay, so let's take a look at the following example here. Oops. Okay, I believe I have two graphs I here. Okay, so they are all the same. Okay, sorry about that. Okay, so now let me go ahead with this example. Okay, so given here we have graph and locate the foci. So we have here the x squared over 36 plus the y squared over 4 is equal to 1. Like I mentioned, the bigger denominator here would be the a squared. Okay, and of course, now the b squared would now be the smaller the denominator. Okay, in this case it is 4. So now we can say that a squared here is equal to 36 and then b squared is equal to 4. Okay, wherein if we are to get the isolate the a and then b here, this would now be, okay, getting the square root on both sides. So that's going to be a is equal to plus or minus square root of 36 is 6. And then same thing here, getting the square root on both sides. So we are going to get b is equal to plus or minus 2. Okay. All right. So next thing is to solve for the value for c. Because remember, the value for c here, okay, the value for c here is actually would tell us the location of the foci. Okay, the value for b would tell us the location of the endpoint of the minor axis. And then of course, the value for a would tell us the location of the endpoints of the major axis. Okay, so now let me go ahead and proceed solving for the value that would locate the foci. Okay, so in that case, we will be using the formula, which is the c squared is equal to a squared minus the b squared. Okay, so in this case, we have here a squared is 36, b squared is 4, so that's going to be equal to 32. Now, getting the square root on both sides right here, so we're going to have c is equal to plus or minus 4 radical 2. Okay, just for the sake of me locating this value in the graph, this is approximately equal to 5.7. Okay, all right, now going back with the idea on how to visualize as soon as you see this equation, how do we visualize that? Is the major axis a horizontal or a vertical? And like I mentioned, just look at the denominator here. Since the denominator is bigger below the x variable, meaning to say it has something to do with the x-axis, and the x-axis we all know it's a horizontal line. So therefore, our major axis would be a horizontal line. And what does it mean with the location of the foci? Meaning to say that the location of the foci is along with the major axis that is a horizontal line. Okay, so that means to say that the point here, okay, before I'm gonna give the ordered pair there, okay, so since once again that the b represents the endpoints of the minor axis. A represent the endpoints of the major axis. And we have mentioned that it should be a horizontal line for the major axis. So that's going to be a -6. So 1, 2, 3, 4, 5, 6. And a +6 on this side. So this would now be your two vertices. So -6, 0, 6, and then 0. And then for the endpoints of the minor axis would be at +2. So this is 0, 2. And then at -2. So this is 0, -2. All right. And so this value would represent the location of the foci, okay? So this is ±4 radical 2, so this is approximately equal to ±-5.7, so that is close to here, okay? So that's gonna be -4 radical 2. I still gonna write this in exact value. We always want that exact value. Okay, here approximately equal to 5.7, but if I'm going to write the ordered pair, I'll be writing the exact value. Okay, all right, so now it's time for me now to connect those points. Remember, the points that we are connecting here are the points of the endpoint of the minor and major axis. So and that's gonna be this point right here. Okay, all right. Okay, so there you go. So those now would be our, this would now be our graph based on this given equation. Okay, now let's take a look at the next example for this. Okay, so we will just be adding a little bit, you know, computations that would apply your algebra skills. And this would now be the 16x squared plus 9y squared is equal to 144, okay? So remember, according to the standard form of the equation of the ellipse is that the constant term here that is isolated on one side, we make sure that if this is always equal to +1. I'll say that once again, you have to make sure that according to the standard form of the equation of an ellipse, make sure that the isolated constant term here must always be equal to +1. So if that's the case, then I need to divide everything by 144. Okay, so this is now equal to, okay, let me write it on this side. Okay, so now we have a 16 over 144. When you simplify that, that's gonna be equal to 1. I'll divide both numbers by 16. So 144 will become 9, 16 will become 1. So now we'll have x squared over 9. Okay, plus, okay, dividing both numbers here by 9. So 9 will become 1. So I will just have y squared there over 144 divided by 9 is 16 is equal to 1. And by the way, I think I haven't mentioned earlier that when you are working with ellipse, make sure that these two terms with the x squared and then the y squared have exactly the same sign. Okay, and then you do have those quadratic term. Those x and y must be in you should have an x and y variable that is in quadratic term. When we say quadratic term, that the exponent must be highest is 2. Okay, all right, so now we'll go back now with how we visualize this. So as soon as you see this equation, how do we visualize the major axis? Okay, like I mentioned, look at the denominator. Which one is bigger? In this case, bigger denominator or the larger denominator is 16. And so in this fraction, we do have there the y variable, and we know that under the y variable, it is associated with the y-axis, and we know a y-axis is a vertical line. So that means to say that the major axis is a vertical line. Okay, now let's proceed identifying the value for A, B, and then C. We know that when solving for the value for A, okay, for solving for the value for A squared is always the larger denominator, so that's going to be 16. B squared here is, of course, the smaller denominator, which is 9. Okay, and then of course when we want to solve for the C squared, we just need to use the two values for the A squared and then the B squared. Okay, so I'll just be isolating the A and then the B here so that we will know the location of the endpoint of the major axis, which is in this case it is A is equal to plus or minus 4. I just simply get the square root on both sides. And then for the second variable, which is the B, so that's going to be B is equal to plus or minus 3. Okay, and then after that, I'll just be solving for C. We know that A squared is 16, B squared is 9, so that's going to be equal to 7. And then of course, this is once again C squared is equal to 7. We need to completely isolate the C squared here or isolate completely the C. So therefore, we will have C is equal to plus or minus the radical 7. Okay, and again, for the sake of me locating that radical 7, this is approximately equal to plus or minus 2.6. Okay, so again, remember, this value of A is the endpoint, are the endpoints of a major axis. The value for B are the endpoints of a minor axis. And then for the value for C, this would be the location along with the major axis, which would be the location of the foci. Okay, so now let me go ahead with this graph right here. And so you'll have here that the major endpoints of the major axis is plus or minus 4. We have mentioned earlier it is a vertical line. So we have here 1, 2, 3, 4. And then for the down here, it's negative 4. And then for the minor axis location is plus or minus 3. Okay, negative 3 here. So let me just label each of those. So we have here 0 and then 4. We have here the 0, negative 4. And then here we have a negative 3 and then 0. And then on the other side here we have the 3 and then 0. And then remember that the value for C here would be along with the major axis, since this represent the location of the foci. Okay, and remember foci is always along with the major axis. Okay, so it's around 2.6, so 1, 2, so around here. So that's gonna be 0 radical 7. Like I've said, I will always be writing it in an exact form. So 2.6, okay, negative 2.6. So this is 0, negative radical 7. Okay, and then again, we will be connecting those endpoints of this ellipse. Oops. Okay, so there you go. So this would now be our ellipse given the equation 16x squared plus 9y squared equals 144 with a standard equation, which is x squared over 9 plus y squared over 16. Okay, all right, now moving on to the next example. Okay, so again for the next example that we now find here the standard form of an equation of the ellipse with a foci that is a negative 2 and then 0 and then 2, 0 and then vertices at negative 3, 0 and then 3, 0. So first, let's go ahead and visualize where those points are located. So if I'm going to draw x and y axis here, so we see that this plus or minus 2, it's over here. Okay, so these are the foci. Let me just write it as F. Oops. Okay, so let me say this is our f. Okay, and then we have here the -3, which are the vertices. Okay, so since we are creating here like a horizontal line along with this vertices and then the foci, then therefore the denominator of x squared therefore should be bigger than the denominator of y squared. Okay, so if that's the case now, let me just go ahead and do a squared is equal to. So we know that the value for a are the endpoints of the major axis, and we know that the endpoints of the major axis would be the vertices. Okay, so that's gonna be plus or minus 3. So that's gonna be plus or minus 3. So that is equal to 9. And then for the endpoints of B, that would be for later. So for now, we know that the value for C is a plus or minus 2. So we have here the C squared is equal to, so plus or minus 2. Okay, let me see. So we have here that plus or minus 2 squared is equal to 4. Okay, all right, now the only thing that we want to know here is the value for C, because remember when you are completing the standard form of the equation of an ellipse is x squared over a squared plus the y squared over b squared is equal to 1. Okay, and then again, I already have written a squared here below x because we agreed that the major axis is a horizontal line that has something to do with the x-axis. That is also relatable with the x-axis, which is a horizontal line. Okay, and so now we need to solve for the b squared. Okay, and then we know that the formula, okay, I'm just going to go back with the formula, is c squared is equal to, we have there a squared minus the b squared. Keeps on doing this. Okay. Okay. All right. So in this case, since we're solving for b squared, so we'll just isolate that later on. So we have here 4 is equal to 9 minus the b squared. Okay, so and then I'm going to subtract both sides by 9. So I'm getting a -5 here is equal to negative b squared. So multiplying both sides by negative sign. So this is 5 is equal to b squared. And so now we're done. We have achieved the value for the b squared, which is now equal to 5. Okay, so we can now write the standard form of the equation that x squared over 9 plus y squared over 5 is equal to 1. Okay, so there you go. That would now be the equation of the ellipse. Okay, so now let's go ahead and proceed with the next, okay, equation. Okay, all right, there's the next concept. Okay, so the next concept here is about the ellipse not centered at the origin, because you notice that all of the examples that we went over here are ellipses that are at the origin. Okay, so now what we will have now are the ellipses that are not centered at the origin. So far, once again, we assume the center is at the located at the origin, but what happens when the ellipse is shifted? Okay, so the equation becomes that the horizontal major axis would be this equation, that x minus h squared over a squared is equal to y minus k squared over b squared, which is equal to 1. And then, of course, for the vertical axis, we will have the vertical major axis. We will have the x minus h squared over the b squared plus the y minus k squared over a squared. So there's not a lot of difference from the previous concept. It's just that we are adding a value for h and then the k, h and then the k, okay? So what does it mean with the h and then the k? Here is that the h and k represent the center. Okay, so like I mentioned, everything else stays exactly the same. The only difference is that every important point is measured relative to the center instead of the origin, just the way we did from the previous example. So we'll use the summary, okay, of this table as our reference while solving the several examples. Or again, if you know how to visualize, then you can most likely be determining those vertices or the endpoints of the minor and major axis and even the foci. Okay. All right, now let's go ahead and start with this example. So given this graph, let's write an equation of an ellipse. Given here that the center is at 3, -2. Okay, so remember the center here, the given value is at 3. Okay, center is at 3 and then -2. Okay, and then so we know that this is the value. Okay, so this is now the value for h, and then this is the value for k. Okay, so now as we can see here that the major axis is elongated horizontally, so that means to say that the major axis would be a horizontal line. So therefore the equation of the ellipse would be x minus h squared over, below here must be the a squared, which is the larger value in the denominator, plus the y minus k, and then squared over the b squared, which is equal to 1. Okay, in this case, we know the value for h. Okay, it's 3. We know the value for k. We know it's -2. The only thing that we do not know here is the value for the denominator. And since we are given here the graph here, we can just simply count, okay, or measure the distance between the center and then one of the vertices. Okay, and then that would be the value for a. Okay, you just need to square that, and then that would be your denominator then. Okay, so let's go ahead and identify the value for a squared. Okay, so that a squared here would be this measurement right here. Okay, and the measurement here is 1, 2, 3, 4. So this is equal to 4. So therefore, this is 4 squared, which gives you a 16. Okay, and then for the b squared, like I mentioned, b has something to do with the distance between the center and the endpoints, one of the endpoints of the minor axis. And then as you can see here, this would now be the distance between the center and one of the endpoints of the minor axis, which gives you 2 units here. So therefore, we have 2 squared, which is equal to 4. Okay, so there you go. Those are all the information we need. So let's go ahead and substitute those values. So now we have here x minus 3 squared over a squared is 16 plus y, and then k is, where's k? Okay, positive 2. Again, I'm making them different sign because according to the formula, it should be opposite of h. So that becomes -3. Opposite of k. So that's going to be positive 2. Over b squared is 4, which is equal to 1. And there you go. We now have written a complete statement for the equation of the ellipse given this graph. Okay. All right, now let's proceed with the next example. Okay, so for the next example, let's go ahead and graph the x plus 1 over x plus 1 squared over 9 plus the y minus 2 squared over 4, which is equal to 1. Okay, so once again, we should already know how to visualize where the major axis here. And since we do have here a larger denominator which is below that x variable, then therefore that's a clue that means to say that x, remember x is a horizontal axis, so that means to say the major axis would be a horizontal line. Okay, all right, now I'll start by identifying the center. So we have here the center. It would be the value for the h and then the k, and then remember to change their sign, because according to the formula this should be x minus h, y minus k. So that means to say when we write it in an ordered pair, we make sure we are changing their sign. Okay, so next one, we now determine the information for the major axis. Okay, so let me write that. Major axis. Okay, so major axis here, we know that the major axis has something to do with the a squared, and a squared here is equal to 9. And so, again, getting the square root on both sides, so we get a is equal to plus or minus 3. Okay, and remember, since the major axis is a horizontal, it's along with the horizontal line, so that means to say that we will have to add or subtract this value of plus or minus 3 to the value of x coordinate from the center, because remember from the previous examples that we are working always at the origin, and so whatever the value here, that would be the x value, but in this case it's not at the origin, so therefore this value for the major axis, since it's a horizontal line, then therefore we need to always add it to the x coordinate of the center. Okay, so now let's go ahead and add that. So the points here would be now the -1 and then plus 3. And then we have here, of course, we need to keep that value of y. And we have here that -1 and then again minus 3. We have here 2 coordinates. Simplifying this, we now have a +2 and then a 2. And we have a -4 and then a 2. Okay. All right, so there you go. This would now be the location of the endpoints of the major axis. Okay, now I'll proceed with the endpoints of the minor axis. Remember, the minor axis would be perpendicular with the major axis. Okay, so that means to say that we are going to work on with the y coordinate from the center. Okay, but before that, we need to identify that value of b squared. Okay, since b squared is again has something to do with the endpoints of the minor axis. Okay, so b squared here is 4. So that's going to be b is equal to plus or minus 2. So similar with the major axis, we are going to add the plus or minus 2. But instead with the x coordinate from the center, we will be adding this plus or minus 2 with the y coordinate. Okay, since it's a vertical line. Okay, so now we will have that, we will keep that x, 1, and then we'll have 2, and then we have plus 2, and we have a -1, and then 2, and then minus 2. Okay, I got it from there, plus or minus 2. So now simplifying this, we have a -1, 0, and we have a -1. Oops, that's not 0 here. Let me just correct that. Of course, 2 plus 2 is equal to 4. Okay, there you go. Okay. All right, so next one, we now have value for, the ordered pair for the major axis, minor axis, and of course the ordered pair for the center. Now the last information that we want to know here are the ordered pair of the foci. Okay, so we know that the foci is simply the value for c squared, okay, or the c. So we will now be solving for the foci, okay, given that the formula is c squared is equal to the a squared minus b squared. So this is now, we know that the a squared is 9 minus the b squared is 4. So that's going to be c squared is equal to 5. And getting the square root on both sides, so this will now be c is plus or minus radical 5. And then again, for this one, we will now be, of course, this is not yet the ordered pair of the foci, but rather, remember, foci is always along with the major axis. So therefore, we are going to add and subtract this value of c to all of the, to the x coordinate of the center, just like what we did with the endpoints of the major axis. Okay, so that's gonna be now a -1, and then plus the radical 5, and then we'll keep that y coordinate, and we have the okay, let me just move it up there so we do have a space when graphing. Okay, all right, so now we'll have it a -1, and then minus the radical 5, and then 2. Oops, change that color. Okay, so as you can see there, I just added the plus and minus radical 5 to the x coordinate of the center like I did in the major axis, because we all know that this ordered pair and then the ordered pair of the foci lie on one straight line. Okay, all right. So now let me just approximate this just to locate it in the graph. So this is around -3.2. No, it's the other way around. I solve the other one. Okay, this is around radical, around -3.2, and this is around 1.2. Okay, all right, so now let me go ahead and plot the points. Now I have now completed all the information I want in order for me to complete graphing the ellipse. Okay, I do have the endpoints of the major axis, the minor axis, of course the center, and of course the foci. Okay, so I'll start with the center, -1 and then 2. All right, next one, we have the major axis, which is at 2, 2, and then -4, 2. And then we have here the endpoints of the minor axis. We have a -1 and then 4. Oops. And then here, -1, 0. And then we have the approximately 1.2, so somewhere here. These are the foci, and then -3.2, so somewhere here. Okay. Oops. Let me change that. Okay, let me just draw the major axis here. You will see, and then the minor axis. Okay, let me just go ahead and label each of those points. So we have here the -1, 4, -1, 0. We have the 2, 2. And then we have here -4, 2. And then here would be the -1, oops, -1, negative radical 5, and then 2, and then the other one would be -1 plus radical 5, and then 2. Okay, I have now complete information that are labeled on the graph. Okay, all right, so this is everything for this example. Okay, now I'll go ahead and proceed with the last example, which is, again, we'll finish this section with an application. So We know that there are many real-world structures, including, for example, the tunnels, the bridges, or even the satellite orbits. And even the architectural designs are modeled using ellipses. So in our example here, we will model a tunnel entrance using a semi-ellipse. I mean to say half of the ellipse. So we'll determine whether a delivery truck can safely pass through the tunnel by first creating the equation of the ellipse and then checking the height available at the truck's width. So again, this example, as you will see that it demonstrates how equation of ellipses can be used to solve practical engineering problem. Okay, so let's go ahead and start with that. Okay, so I'm gonna go ahead and start with, of course, an illustration here that is something to do with the tunnel. So for example, this is the ground. Oops. Let me use a ruler here. Okay, so for example, this is the ground. And then I'm going to draw now an ellipse, semi-ellipse. Okay, let's say, oops. Okay, so for example, this is the tunnel. Okay, all right. So for example, this is the entrance of the tunnel. And so it says here that the tunnel is 16 feet high and then 14 feet wide. Okay, so let me just draw that. So the height here is 16 feet. And then the wide or the width of this tunnel is 48 feet. Okay. All right, next one. The question here is that will a delivery truck that is 14 feet wide and 15 feet tall safely pass through the tunnel? Okay, and then we'll justify our answer using, well, this mathematical model, meaning to say the equation. Okay, so first thing is I want to know the exact location in terms of a coordinate and an equation of this tunnel. Okay, and we know that again the equation of an ellipse would be an x squared, okay, over the a squared, since this obviously here the major axis here is a horizontal. Compare it with a minor axis. If we are measuring the minor axis here, the minor axis, the b squared here is 32. Compare it with 48. So obviously this one is larger. So I can say that the major axis is a horizontal. Okay, so plus y squared over b squared is equal to 1. Okay, all right, so now we have here the x squared over, we know that we are just getting the half, okay, the distance from the center. Let's say this is the center up to the endpoint of the one of the endpoints of the major axis. So this would now be that a is equal to half of this. Okay, so this would be just the measurement that we want, and that is 24. Okay, so therefore a is equal to 24, and so b is equal to, this is already half. Okay, 16. Okay, all right, so next we now get the a squared and then the b squared. So that means to say that a squared here is equal to 576, and then b squared here is equal to 256. So now we can now substitute those values. So we get 576 here plus the y squared over 256 is equal to 1. Okay? So now this equation represent the exact location. Well, if you're going to look at is as if it is in x and y plane. Yeah. So we have here the exact location of this tunnel would be this equation. Okay. Now the question here is that will the track can enter that without bumping the tunnel. Okay. So in this case now, for the sake of again simplification, of course, of the track, I'm just gonna go ahead and draw a track that is a rectangle. Okay, so let's say this is the track. Okay, so let's say this is the track, and then it says here that the track is 14 with, okay, let me just a little bit realistic there. Okay, it's a little bit rectangular in shape. Okay, so let's just say this is the track that it is 14 width wide. So this is 14 feet, and then the height is 15 feet. Okay, again, the question here is that, okay, will it bump on this portion right here? So I'm going to use the width of the track, okay, which would be that x now over here. Okay, x here is equal to, keeps on doing that, sorry about that. Okay, so I'll probably, this point right here, okay, the x here is equal to half of that 14 is 7. Okay, we have here 7, -7 there on that side. Okay, so I'm going to use that exact value of x and see what would now be the value for y, or the height of this ellipse. Okay, so we on this particular location, that x is equal to 7, which is again the width of the track. Okay, so now I will be creating now an equation related to this and see what value of y would that be at this exact location of that track. Okay, at the end of the track. So that's gonna be now, again, I'll be using this equation, but now x will now be 7. So 7 squared over 576 plus the y squared over 256 is equal to 1. Okay, so now we know that that is 49 over 576 plus the y squared over 256 is equal to 1. I'll subtract both sides by 49 over 576. Now we get a y squared. Let me move that. Okay, now we get the y squared over 256 equals 1 minus 49 over 576. Okay, so now we will have here subtracting that. Okay, so we have 1 minus 49 over 576. We get, okay, so I'll go ahead and move on this side. So y squared over 256 is equal to 527 over 576. Okay, now I'll cross multiply that. Oh no, I don't need to do that. Okay, I'll just multiply both sides by 256. Okay. Okay, cancel. So now we have y squared is equal to, okay, times 256. So now I'm getting a 2108 over 9. Okay, now I'll get the square root on both sides. Definitely I'm not going to get the negative sign, because anyway what we're looking for here is the approximate value of the height that is on a positive side. Okay, this is y 15 point, how many decimal place? It doesn't, okay, it doesn't say here, so I'll just say 1 decimal place. Okay, all right, so now it's 15.3, the 15.3 feet. So that means to say that this height right here, it keeps on doing that. Okay, let me just, Okay, all right, that the height of this portion right here, which is the value for y, is 15.3. And then remember, the height of the track is 15. So the question here is that will a delivery track that is a 15 feet in height, tall, safely pass through the tunnel? Well, we can say that it's yes, because as you can see here, the height of the track is only 15 feet, but then the height of the tunnel at that location is around 15.3 feet. Okay, so again, comparing this, we can now say our final answer would now be yes. Okay, the track will safely clear the tunnel, but I know it's too close, but only about 0.3 feet. Okay, too close, but still can still go through safely. All right. Okay, so again, like I mentioned, this is the final example of this section. And as always, okay, it's your now turn to apply what you have learned from this section or practice, okay? Complete this checkpoint problem. As you work, you need to make sure that you can identify the center of an ellipse. You determine whether the major axis is a horizontal or vertical by looking at their denominator of x squared and y squared, and then find the vertices and foci. Remember, the vertices are the endpoints of the major axis, and then foci are along with the major axis. And then graph the ellipse accurately, and then recall the variables that we have used to represent or that would relate with the location of the endpoints of the major axis, the minor axis, or the ordered pair for the foci. And then, of course, solve a word problem. Okay, and then, of course, definitely graph the ellipse accurately. I think I have said that again. But anyway, okay, again, for today's lessons, like I mentioned, we have learned the geometric definition of an ellipse, the parts of an ellipse, and how to identify the horizontal and vertical ellipses, how to graph the ellipses centered at and away from the origin. So how to write the equation of the ellipses and how ellipses can be used to model real world situation. Okay, so again, as you complete your homework, remember this key idea. The larger the denominator always identifies the direction of the major axis, which represents, again, which we are using the variable a. Again, if you consistently identify the center first and then locate the major axis and then the minor axis, graphing ellipses, I would say, become much more straightforward. Okay, so once again, thank you for watching, and I'll see you in the next lesson as we continue exploring the other conic section.